So we'll get started on this very last lecture, and it looks like you have still survived. At least you are, your eyes are open, so that's good. Huh?
We enjoy you.
All right. So this very last lecture is also the most colorful one. Because this has to do with plastic and organic solar cells. Sounds very interesting. And what I'd like to tell you is that although it's at the end just a solar cell, p-n junctions, electron holes coming out in respective contacts, but the idea and the innovation that lies under this technology is something that is very beautiful, and I hope that you will appreciate it. It's not just something that could come it requires a very sort of deep insight about how electrons and holes flow in a system. So let me get started. So I'm going to talk a little bit about that why organic solar cells, but by now you know that we want to reduce cost, and what could be less costly than going into sort of Ace Hardware store and buying 2 cans of paints. If you could buy it, mix them up, and can make a solar cell by painting on something, now that would be great. That will be cheap, you can buy it in Walmart. So that is what the argument is, that it will be a very, very cheap technology. In practice, of course, nothing is simple. And it turns out that if you go and try to make a cost estimate for organic solar cells, it is higher than crystalline silicon. So actually we are not there yet, and I want to tell you that how one might get there and what the physics is. It's actually very, very simple and very elegant. Hopefully you will see that. I'm going to talk about 3 things. One is the planar heterojunction organic photovoltaic. That's the word OPV mean. Organic, some people will call, instead of organic, they will call it plastic photovoltaic. Now, then they'll talk about checker box heterojunction. And the most important one is something called a bulk heterojunction devices. Now the word heterojunction, as you might realize, that this will involve in some form 2 materials that are going to do something special for this device. You don't see any word homojunction floating around here. So that must mean that you need 2 materials at least. It cannot be, silicon is a homojunction. There's no hetero in there. So we'll be seeing there's something called 2 materials play a very important role in here. And then I'm going to connect it with percolation, fluctuation, and efficiency limits, and then conclude. So again, this picture you have seen, and the basic argument is that p-n junction crystalline solar cell is very important, 80% of the market, maybe more, but it's relatively thick, very weak light absorber. So we are looking for thinner structures, and the thinner structures, of course, the one I talked about in the previous lecture had to do with this PIN structure. You remember electron hole partitioning, electron going at the right contact or falling off through the wrong contact, and the partitioning and how you sum them up and understand why the current is not independent of voltage. We will discuss that. Now I'm going to talk about this, but first of all look at this. This looks horrible to begin with. There's this 2 plastics inside one another, and I don't even know how to even begin thinking about this structure. At least this looked reasonable. This doesn't look reasonable, and so how would you do a theory on unreasonable things? And moreover, look at this structure. This is not even flat. It's carved on something and also colorful. And the question is then, how are you going to think about a structure that doesn't really look reasonable? So very quickly, in terms of the efficiency limit, this is what people say. Generally, steel probably $1.36 for the OPV, and this is not by any means cheap currently. And the reason it is not cheap is because although the material you will see is very cheap, it's like a $6 per kilogram. That is how cheap it is. But that it turns out that by the time you put in the glass encapsulation, the mirrors, the ITOs, the other things, encapsulation and all those things, price goes up very quickly. And most important reason why the price goes up is because the reliability is horrible. You'll be lucky if it survives a year. And then, so therefore, the hope is that if we can do something that will have 15% efficiency and will last for 15 years, now that will be an unbeatable technology. So this is where, this is not a current technology. This is something, it's a hope for the future, but we'll see why people are so excited about it. So let's talk about planar heterojunction. But before I do that, I'll have to tell you something about something called an exciton. Now, you might not have heard this term before, now, but you can immediately see that when Professor Lundström talked about solar cells, there was something that was a little fishy. No, I mean, it was correct, but it was a little fishy. And the fishy thing is this, that when you have an electron-hole pair generated due to an incident photon, we immediately thought that if you apply an electric field, the red electron goes to the left, the white holes go to the right, and I have a photocurrent. But if you step back 1 second, you can immediately realize that that doesn't sound right. Because this electron is negative, this hole is positive. Is it possible that they should immediately go apart from each other? I mean, this is, if you think about hydrogen atom, you wouldn't really say that they will simply fly out from one side to another, because you would say, no, in this case, there's a Coulombic attraction between them, this red electron and white hole, and they'll be circling each other, right? That's why you have a hydrogen atom. So in that case, why didn't you ask that question in here? Because that should have been circling each other also, a positive and a negative thing. Now it turns out that you can easily answer that question. By the way, so if they begin to circle each other, this electron and holes, if they begin to circle each other, this entity is called exciton. So exciton, you could say that electron plus hole, instead of writing that big thing, I'll just call it exciton. Now, if you look at this bound level for the hydrogen atom, you may have seen in your first course in physics that the first bound level is given by a bunch of constants, and that has 1 over kappa square. Kappa square is a dielectric constant. Now in air, where the hydrogen, the electron is moving around the proton, kappa is 1. So that gives you about 13.6 eV, and they are bound tight. And what is the radius of a hydrogen atom? Of course you know that, because the Bohr radius also you could calculate. And if you calculate that, you will find this is proportional to the dielectric constant. If you put the dielectric constant is equal to 1, then this is about half a angstrom, 0.53 angstrom. So that's why this electron moves around the proton. Now, if you now think about this and apply it to this electron and hole, you will see Professor Lundström was right. Because in silicon, the effective mass, let's say in the order of 0.1, I'm just making up some numbers. Kappa is on the order of 10, it's about 12 or so, but let's make it 10. And if you put these numbers in here, you can see immediately the binding energy will be divided by 100 here, multiplied by 0.1, so it will be 1000. So I will have only 13.6 milli-electron volt. Now KT, on room temperature, is 25 milli-electron volts. So yes, they want to go around each other, but their binding is 13.6. A phonon comes in, kicks them, and they are immediately apart. They are not strongly bound. So therefore, the electron went in their respective contact. Now, if you, on the other hand, think about a polymer, for example, the polymer would be the grocery bag that you get from Walmart. In the polymer, the dielectric constant, unfortunately, is very low, on the order of 3 to 4. So in that case, same formula, same everything, you put it in here. Now, and I'll explain this in a second. If you put it in here, 151 milli-electron volts, many KT, 6 KT. Now, this is not going to go anywhere. They are going to circle each other. and the radius is 15 angstrom. And so what is going to happen, all this pair of electrons and holes, like a little droplet, they will be moving around, charge neutral, negative and positive. They will not care about electric field. They are not going anywhere. So this is exciton. And after a while, they will recombine each other, and you don't have any light coming or any energy coming out. So this is my problem with organic solar cells. So I have to do something special in order to get the electron and hole out, because as electrical engineers, we don't like excitons. That they stay together like this and then they recombine without giving us free electron and hole, right? So this is the problem, so long you understand the problem. By the way, I have assumed this is to be 0.1. In the polymer, along the polymer chain, this number is correct. In the pi stack, the other direction is about 1.75, much higher, because you see hopping is involved. But when you put them, the effective mass, by averaging them, you'll get a number something like this. So this is not unreasonable. So this is the trick. You see, instead of having a single polymer, which is a homojunction, you can say, if I somehow, and nobody is going anywhere, they are diffusing around and not giving me, so I want to break them up. What do I do to break them up? Well, I put a separate material in there. Instead of having one, I put now two. Now it's going to break. Why? Because although this material, so this is the band diagram for this side, this material, you can see that this one has a particular work function, material A. This one has a different work function, and that is the material. So this is B, this is A. And in here, I have an atomically sharp junction, sharper than this 15.3 angstrom, because 15.3 is like 6-7 atoms. So now, if a exciton comes in and gets to this junction, this field like a knife will get inside it and pull them apart. If it's any gentler, like a p-n junction or a pin junction, it is not going to do anything to the exciton. That's why we need a heterojunction, right? Now, of course, if you put it in a heterojunction like this, this thing will diffuse, and when it hits this junction, this electric field will pull them out, and the electron will go this way, the hole will go the other way, and there will be a light output, which is very good, which is what we like. But you see, if these regions, interface regions, are very defective generally. If I don't do something special, these electrons will be moving around and a fraction of them will be recombining in here, because this is a lot of traps here, and that I don't like. So then what do? What I do, that instead of keeping these two metals the same work function, what I can do, I can make one aluminum and another ITO, let's say. In that case, the work function aren't the same, so therefore, this one doesn't care that you have two metals, because this one is charge neutral. So this will diffuse without knowing that there is an electric field. But as soon as it comes in here, this one is pulled out through this electric field, this one is pulled out through the electric field, and now we have good current. Right? So this is how an organic solar cell works. So if you understood this far, hopefully, then the rest of the story you'll be able to appreciate, because without really knowing that, the other pieces doesn't really make sense. So I have this beautiful sun here, and this two material, 3-dimension I'm showing here, two material stack. This is a planar heterojunction because the two materials are sitting and sharing one plane across them. So the junction is a big plane on them. And so when the light came in, it generated this droplet of electron and hole. It was diffusing around until it saw this junction. And when it saw that junction, this went this way, the hole went this way. And in the output circuit, I had the light bulb light up. So this is how a planar heterojunction works. Now the question is, how am I going to understand a structure like this? Cartoon is good. PowerPoint can do this very quickly. But the thing is that if I now have to think about this structure, can I use what I just told you in the last class, last lecture? And can I use that partitioning, going left, going right? Of course, otherwise I wouldn't tell you that it can be done. So let's think about it, how to do it. So what I'm thinking about it, you remember this, for thin film we have this complicated, slightly complicated equivalent circuit. I'll be talking about this one and this one now, a little bit later about this one, and not very much on this one because this is very similar to what we had in the last lecture. So even then we have shunt resistance, nonlinear shunt conductance and all. I'll not be discussing that. So let's get started on the photocurrent, which is supposed to be a constant for silicon solar cells. Now, one thing you can see that how this has a little bit of complicated, that if a exciton is generated here, far away from the diffusion length of this junction, then all of them who have been diffused here, they will all self-recombine, because before they find this junction which will pull them apart, they are very close together. They will recombine, give up the photon or give up the energy, and that exciton is gone. That photon has no purpose whatsoever in this discussion. So the exciton diffusion length, square root of d tau x. And why am I talking about just diffusion? Because it's charge neutral, right? Plus and minus in the droplet, charge neutral. So I should only have to think about diffusion, no drift is necessary. Now, do you remember that I gave an example of silicon solar cells where half of it was diffusion, half of it was going to the left junction, and half of it was going to the right junction with the blocking layer and all? I wanted to explain how that works. So I have rotated the diagram 90 degrees. So what I'm trying to show here, that any exciton, this is exciton profile, any exciton that is generated in this region, they go and get dissociated in here, the right contact, because that's where I want it to go. On the other hand, a bunch of them can go and recombine, get dissociated at this contact, which is also a heterojunction, but that's the wrong contact to get out of. So the only one that will be useful for me is the flux associated with this one. So let's calculate how much flux is. This is how many excitons will produce electron and holes. So again, I'm using the same formula that I have. You may remember this W, I put 4Lx. If it's thin, then W is the whole thing, W over 2 is this, and if it is very thin, then it will be W over 2, which can be collected from this side, because the other half will be essentially collected from the other side, and it will be completely useless. Now, think about how I can do the partitioning argument. So my electrons and holes have just been created. These electrons have two options. They can go, or they can loiter around a little bit, and if they find a hole close to the interface, they can recombine through the holes. So how will I do the partitioning? Very simple. You remember this formula? This is the how many electrons are going flux that is going to the left contact, gamma ln, and I have this recombination that's telling me what is the recombination with this quantity, with the holes. And I have gamma Rn, any flux that can jump over the barrier. Now, most of the time, the barrier is so big, I'm going to ignore it. So therefore, most of the time, I shouldn't have to worry about that term. So I drop that term. Now, what about the holes? Should I not have to worry about this term? Well, you can see this barrier is so big, the holes cannot come out here. And so I get rid of this, it is 0, so whole term goes to 0. Right? That's that simple. Now, when this one comes out, what is the flux? Mu times E naught. E naught is the electric field here. That is the flux. It is going to come out. No barrier in front of it. If you use the electric field, it's just going to slide down the hill and essentially be collected. On the other hand, if you have gamma recombination, this is a simpler expression. It simply says it depends on the recombination time constant associated with it. And if you have a lot of trap, the time constant will be low, and so that will be your recombination rate. You can put it in. If you put it in, then mu E naught and mu E naught plus S. S is the recombination, interface recombination, and that immediately tells you that this current cannot be voltage independent. Do you see why? This electric field E naught is the electric field here. That electric field is VBI minus V is the applied voltage divided by Wn. This is the Wn. And as I am changing V, my E naught is changing. If my E naught is changing, this ratio is changing. And this J exciton is independent of field, but J photon cannot be independent of field. If the field is high, they are rapidly getting pulled out and no recombination, very little recombination. If the field is low, they are sort of loitering around next to the dangerous junction and a huge fraction is recombining. So therefore, this current, photocurrent in the beginning will be high, gradually it will be low, and eventually it will be essentially equal to 0 if you have this process continuing. Now, in general, of course, instead of just Shockley-Reed-Hall type recombination, if you have a bimolecular recombination, you have to work a little harder. You have to say, write one more line of algebra. You have to say that the exciton current that is coming in is equal to the recombination flux at x equals 0 plus any Shockley-Reed-Hall type recombination multiplied by this drift flux. And if you add them, you can see this is a quadratic equation of N0, and even I can solve quadratic equation. And so therefore, the photon current will be related to the exciton one, and you can put it in. Again, this will not be voltage independent. Why? Because the voltage is sitting in this Vt. It has mu times E naught, the electric field, and the E is changing with voltage V, and therefore the photocurrent is absolutely dependent on voltage, right? So that's the important piece. So this interface, and we'll come back to this interface recombination is a big problem, because think about it. If I didn't have this interface recombination, if this were 0, then this would be 1, and I could get every exciton that has been generated. I could collect them all as output current. And this interface recombination is causing me the problem, and that's what we'll need to work on to reduce. Okay, so that's all I had about photocurrent. You see, very simple, that a fraction of this electrons, the exciton that are here gets dissociated, and only a fraction can get out depending on this, how many recombine at the interface. Now, if you wanted to look at dark current, remember dark current is very important. Again, here it's very simple calculation. Why? Because dark current, remember, I don't have any, do I have any exciton? I didn't shine light. So therefore, no electron-hole pair were generated close to each other. And if there's no electron-hole pair generated close to each other, then of course, I cannot have any exciton, and therefore, there's no exciton in the dark condition. Now in this case, again, if this is the only recombination mechanism, how would you calculate this total dark current? Because there's no other place to go. It cannot go over the barrier. The barrier is too high. And therefore, all you need to do is to find out how many electrons you have at x equals 0 and how many holes you have x equals 0, multiply the gamma, that's the recombination rate. You can easily calculate that how many can climb up over this barrier, and that how many, this is the voltage, Q electric field multiplied by Wn, exponentially suppressing the number of electrons that are on the left contact. So only a few can climb up, right? Climbing up is difficult. And similarly for the holes, a few can climb up because the hole doesn't want to go down. So they want to, a few can climb up, and this, and essentially you can get an expression. And where did this VBI minus V come from? Well, again, from the electric field. You remember that the electric field had this VBI minus V divided by the distance, so that's where it came from. Anyway, so once you plot this current and this simple local expression, and you do an exact numerical simulation, they'll be very close. We don't really care about this region, because that's what I'm going to show, that essentially this region is sufficient to explain the IV characteristics of an organic solar cell. Okay. Now, before I go any further and compare it, maybe I want to step one step back. One thing I want to make sure that you understand, that this is a very special solar cell in the sense, because the electrons didn't go here, they cannot climb up and go here, right? Because they didn't go here, each region has just hole or just electron. It cannot have both. This is very different than other solar cells. Remember the silicon solar cells. The electron was going this way, the holes were coming this way. If you took a microscope and wanted to look at one point, you'd find both electrons and holes sitting there, right? They are going in different directions. Not in here, because look, these holes are, electrons are coming out here, but there's no electron here. and on the other no holes here, I'm sorry, lots of electrons, no holes here. Similarly, this band gap is big, no electron came up here, so essentially I don't have any electron over there. Just one type of carrier in respective regions. This is very important. That's why even if this region is highly defective, you will not have any recombination. All recombinations will only occur at the interface, right? So low quality material that will still not have any recombination. Okay, so you can, take these equations that I already told you, excitant flux 2 slides ago, photon flux from the excitant flux to 1 slide ago, and then this is the dark current I told you about. You put them all in, and this is the total current. And this is the approximation, the blue current, and the red one, you do it by, if you solve big complicated differential equations, second order and all, they'll be almost correct. They'll be almost correct, so that says that we have caught most of the physics, except that if you go in and solve for numerical simulator, you will see, like ADEPT that Professor Gray talked about yesterday, you will see that this is what the thing is saying that it should be, whereas I am saying that this should be the flux based on this. So what is it that went wrong? You can immediately see this has horrible fill factor, right? Fill factor is, remember, because the analysis people are lazy, so there is this green small box that you set in with respect to the big box, and so here the fill factor is actually pretty low, 0.5, maybe even 0.5 or 0.6, pretty low. And what happened then? So you can easily understand what happened, and that's why you should not be using planar junction most of the time. What happened is the following. If this is the band diagram. Remember, this is this version that I wrote, draw in a cartoon, on a PowerPoint cartoon, but if you do really a numerical simulation, what you will see, this is the band diagram. This is V equals 0, a lot of high field, and as you push the voltage up, then gradually this curve gradually goes up and the field is reduced. Yes, the field is reduced, but you can see the field is not constant. And why is the field constant? Because I assumed the field is to be constant. Look, here I have constant, the cartoon diagram has constant potential, that means a constant field. It's not a constant because of that issue, that only one type of carrier is in respective materials. So as soon as the electrons are trying to get out from this region, all the pre-existing electrons in here, they are saying don't come. This is a self-consistency problem because they have all been piled up in here. They are saying they are trying to repel it. As a result, the electric field is low, so it's not getting collected as efficiently. So you're putting a voltage, but the voltage is not reaching the junction. And therefore, now the field is low, electrons moving around, and it loses a huge fraction of those electrons by recombination in this here. Because you're not supposed to stay here. You're supposed to get away from this region as quickly as possible. All right, so this is how a planar heterojunction works. But of course, that is not why I said that this is beautiful, because it's not, so far it doesn't look very beautiful to me. But we want to do more. But one thing you realize, that if we could sweep the electrons out quickly, in that case they wouldn't build up to such a high value, will not be able to screen the electric field this way. And as a result, in that case, if I had high mobility, then my approximate formula should become better and better, right? Because then the constant electric field assumption will be correct. And that is indeed the case, because if you do the numerical simulation just with a little bit high mobility, this mobility is 10 to the power minus 4, this mobility is 10 to the power minus 3, and in that case you can see it immediately approaches the analytical solution because the approximations are now better done. See how low the mobility is. The silicon mobility would be hundreds of times or 1,000 times more than this, right? Look at how this is 10 to the power minus 3, 10 to the power minus 4. Cheap material has low mobility. So that is expected. So what's wrong with this planar heterojunction? Why it looks like we can do these things? The main thing that is wrong is that only a fraction of these excitons can be collected, and all these excitons that were generated, they essentially self-recombine as if they were never born to begin with. So it doesn't really matter. So all of them are lost. So that's not a very good condition. So what can you do? So what you can do is you can say, well, I'm an electrical engineer, so what I'm going to do, why not make this region comparable to this, right? So that it's just square root of d tau x. And this is then, it will be like 15 to 20 nanometer. And in that case, I will collect everything. But of course, you realize, if you try to do that, then this heterojunction is also closed. It will take away half of your carriers. Wrong contact, wrong recombination. And so you cannot really do that. You have to do something more clever. So what can you do more clever, a little bit more clever? Well, this is what you can do. What you can do is to realize that excitons don't care about electric field. Only thing they care about is diffusion, and the only thing they care about is finding a junction so that they can be dissociated. On the other hand, electron and hole, they care a lot about electric field. So why don't I make them orthogonal? Because if I make them orthogonal, then probably I don't have to keep the considerations coupled. So I can make them orthogonal this way. What I can make is material A and material A, these two heterojunctions here, and the white region is material B. Now, no matter where the exciton is generated, it will quickly find the junction, but it will not go and touch these wrong contacts. It will essentially just be dissociated in here. And once it is dissociated, then the electrons and holes can be pulled apart. So this is, let's say, this is electron highway. So they will remain in electrons, in the electronic material. And this one is a hole. So they will stay with the whole material. So this is like really a divided highway. It's sort of a semi-classic analog of this the spin effect, right, where the K and minus K gets really spatially separated. This would be the semi-classical analog of it, because now the electrons and holes, they are going in the opposite direction and not talking to each other. Except they will recombine when they meet at the interface, which we don't like. So people are already making such cells. You may say, how do I make this checkerboard structure? People are making it. What you do is, there are many schemes. So you can have a bunch of nanowires or nanopillars of one material and coat it with the other material, so that in between the second phase comes in, and if you shine light on it, then essentially if it's the organic structure, in that case the holes, these pillars will carry only electrons, the other one will carry only holes, and then they will get separated in their respective contacts, right? And the excitons will be dissociated, because look at the surface area. Huge amount of surface area associated with it. They will quickly find a surface nearby and they will be dissociated. Very good. Now, of course, this will be costly to make. You can make, so the RE is going to be cost effective with silicon solar cell, maybe not. But the idea, look at the idea, what they did. They make the exciton and the electron go in orthogonal direction. That is the trick here. So you can do some analysis. You can do some, this is my checkerboard in 3D. PowerPoint is very good, I see. So you can quickly calculate number of fingers you have. Fingers are these red fingers. And this is 1/2s², the number of fingers, because you see half the volume is blue and half of them are red. So you have to do a half and then a s² in order to know the number of fingers you have per centimeter square, right? Because the red is half of the total volume. And the volume of each one of them is this red volume, which is ws², is the volume of each finger. If the electron hole pair excitons are generated here, only the ones which are within square root of dt, within this junction, they will be separated. And the rest which are sitting in the middle, they will self-recombine. They are not coming out. So I don't have to care about them. So if you want to know what fraction of the charges are going to be collected per finger, well, you have 4s, 4 sides, but of course it's being shared. And so you have a factor of 2 here, and s², because you want to know the fraction, s² is the area, and only this fraction is getting collected. This is the diffusion length. So 4S is the perimeter multiplied by distance. This is the area of this white region. Remember, if you want to put a garden next to your backyard and want to calculate what fraction of the area, you just multiply things like this. And then once you do that, you can see how much the total charge collected will be. This is how many excitons you will collect, and you can see that it can scale with the number of fingers or how small you make the individual fingers. So your efficiency can really go very high. That's why you should do nanostructuring here. And without nanostructuring, actually, organic solar cell is not going to work. And again, these things you can easily do. Electron in one highway, holes in another highway. You write down the formula. Let me not go through it. You can go through the dark current analysis and essentially make an approximate calculation of how many electrons and how many holes are you going to collect. Here, I have to account for the recombination as the electrons are coming out through their highway and the holes are going in the opposite direction. If they meet in the interface, they are going to annihilate each other and not going to come out of the structure. And so you have to account for this recombination. But other than that, you can essentially use the very similar partitioning argument and very similar expression for current. Okay, so now comes the last part, and the last part hopefully is what people actually do, which is much more interesting than what I told you so far about. What they do is that they don't have these pillars, they don't have this type of planar heterojunction. What they have is two materials, they'll put it in somewhere, mix it up, put it in an oven, and out comes the solar cell. This is what this is. Look at this, green is one phase, the other material is this other color is another phase, and they are inside each other, tangled, bundled, and you cannot tell one phase from the other. And the question is, how are you going to think about that? And it turns out, hopefully you will understand, that it's easy to think about it. Because you can think about what it did. What this one does, this random structure does, is exactly what this one did. Because the structure is so random, no matter where the exciton is generated, it is quickly find a junction. If it finds a junction, it will be pulled out here, and it will be pulled out in the whole carrying region, and they will be separated, and you will have a photocurrent. Look at the area. This area was a planar area. In many of the gels and in other things, the area per centimeter cube, if you mix it very well, and each domain is a micron size, the area could be 2 football field size per centimeter cube volume. That is how big this surface area has become. Every exciton, essentially close to 100% of them, the light that came in, everybody will be dissociated. This is how efficient organic solar cells these days are. Exciton part, of course, we have to pull them, bring them out. That's the second question. But at least getting them dissociated, no problem. So let's talk about bulk heterojunction. Now, what is this word bulk? The word bulk comes from the fact that this heterojunction is distributed within the bulk. It's not on the surface, or not on the planar, not on the checkerboard. It is distributed within the whole volume, and that makes it bulk heterojunction solar cell. So let's think about it. How should I think about a solar cell which is so complicated? So this is my chemist bowl of solar cell. I mix polymer A and a polymer B, put some sort of solvent, and then presumably this blue is one phase. I said it will be colorful presentation, so this is the color. And then you put it in an oven, 100-125 degrees C. 15 minutes later, out comes the solar cell. Now, the way it works is something very interesting. What happens is the phase desegregation. Most of the time, if you put salt and water and put it in your microwave, they get homogenized. They don't get phase segregated. But these polymers are such, and their surface tensions are such, that if you put it in here, they like spoiled milk, they get phase segregated. So this is called spinodal decomposition. And here is a cartoon that Bishwajit made, and look at how, as a function of time, how these two structures get phase segregated. In the beginning, completely mixed up. You cannot say which is region A, which is region B, yellow and red, cannot say really. This is not, if you shine a light on it, excitons wouldn't really, they will laugh at this structure because the heterojunction is not really there. Nobody is going to get separated. But after a little bit, if you anneal it, this is what's going to happen. So this is going to get phase segregated. Did you notice two things? One is that as the time progressed, the black and the white, the phase volume didn't change. If you started with 1 kilogram of polymer A and 1 kilogram of polymer B, none of them evaporated. So you still at the end you have 1 kilogram of polymer A and 1 kilogram of polymer B. Nothing changed. That's a very important statement because nothing evaporated. The second is that these regions are gradually getting thicker. So they are bringing their like kind. And if you waited long enough, then this might even become segregated like a planar heterojunction if you use it long enough, if you didn't have any boundary effect, right? Because they want to bring their own kind together. So now, how are you going to describe such a system? I'm going to very quickly tell you what equation was used. What the equation, but not going to explain it very much. The equation that was used was sort of a diffusion equation of some sort. Here is the surface tension, and here is the mobility of the polymers, how they can diffuse across one another. So you can solve this equation, and then once you do that, I think there are recent experiments like this in Nature Materials where they use that high Z contrast. So this is not really two polymers. It's two polymers, but one has, not for PV, one has very high number of protons. Nucleus is very high, so that when you do electron tomography, you can get the Z contrast out of it. So that is how this picture was taken. Very popular. Anytime you want to do three-dimensional complicated structure, this electron tomography, I see it used all the time. So this is how the picture was taken, suggesting that this way of thinking about the material is okay. That's fine. And I will very quickly tell you a little bit, because that's not the essence of the story, that if you start with a completely homogenized structure and then increase the temperature, and then there is a stable point here, and this in the phase, and then stable point here, so that in the black region there is a little bit of white mixed up, and also in the white region there is a little bit of black mixed up, but on the whole these junctions are reasonably short, and so when you put your exciton in here, they will be separated. So it's not a pure phase. It is sort of a little bit of mixture of the other, but it's like 90% white or 90% black. So we shouldn't complain because the junction is maybe a little bit lower than the pure phases, but still it will dissociate things. Okay? Now, what I want to tell you about, this is interesting. Because I think, okay, all right, let me go and see what happened. So the question is that if things look so complicated, then can you do any physics with it? And the answer is that actually you can do a lot of physics with it. First of all, look at this. These regions as a function of anneal time in the oven, how long you have put it in your microwave, that as a function of that, these are getting phase segregated. And people know, and you can do it from simulation also, that this grain size, average width of this region goes as anneal time to the power 1/3. Now, that is the anneal time, so within 1,000 seconds, which is a couple of minutes, then essentially your grain sizes will grow to a certain distance, but it will continue to grow, phase segregate as a function of time. In the beginning, it's a log plot, so in the beginning very fast, but then gradually it will roll off. It will slow down because phase segregation has already occurred. Now you can use this information to do something which you might not have thought possible. Think about it. So the phase is this width of this blue region is W. If I know the width of this blue region, can I calculate the surface interface area of this blue to red? I should be able to, right? Because if I know the width, if I knew the original volume, if I divide one by the other, I know how the interface is going to evolve as a function of time. So let me show you how those excitons, and I'll come back and show you how to calculate those things. But this is a movie that shows how the excitons are generated in the complex structure and how they get gradually phase segregated. They get dissociated at the contacts. So let me show you one more time. So what is happening is that a light pulse came in, they generated excitons in one of the phases, let's say in the this, like a raindrops. It is coming and getting collected on the red phase, and then they are finding the junctions and getting dissociated. Since I had one pulse, they will either self-recombine or they get dissociated at the junctions, and so that is how this pulse comes in. Sorry. What happened? There's something wrong here. Anyway, so let me move on and see how I calculate how the interfacial area is. Do you understand why we are thinking about the interfacial area? Remember that the recombination can only occur at the interface. So if I could calculate how the interfacial area is changing as a function of time, then I could stop in the right moment where the recombination is the lowest. So that's why I'm spending so much time trying to calculate the interfacial area of these complex structures, and which is very easy to calculate, as you'll see. You see, although this one looks very complicated, you can think of it's like two threads. Like my daughter sometimes will take two threads and then mix them up all together. And then you have to unspool it. Now, if you can easily unspool it, let's say, but the volume of the red and volume of the blue, they will remain the same. A little bit later, again, if you unspool it, because these things have gotten wider, this interfacial area will become smaller. And if you unspool it further, of course, getting wider, interfacial area is getting smaller. So in this sense, you would wait till it is very small. That way, of course, you can dissociate them. Interfacial recombination will be very good, very small. So now think about it. What is the interfacial area of this complicated structure? You know the area, original area, divided by 2, because it is 1 to 1. Blue and red was 1 to 1. So area divided by 2. WT, this width, evolved as a function of anneal time as t to the power 1/3. So without doing anything else, despite this complexity of the structure, you can immediately find out how the interfacial area of this one will evolve as a function of anneal time. You don't have to do anything else. Now, how does it help me? I can calculate exciton current based on this in the following way. Remember that only a fraction of the electrons, excitons that are generated can be dissociated, and those has to be within square root of b tau x. That is the part that gets dissociated. The rest of them essentially recombines and they cannot be collected. So I can easily calculate what this Q is. This is the square root of dt. This is how much it gets collected, and L is the interfacial area. So this will be the total charge that is collected. And if you wanted to calculate the exciton current, you do Q divided by tau x. That will be the total charge collected divided by the time it took to generate the charge. And from there you would say the exciton current would fall as anneal time to the power 1/3. And then you will do a complicated calculation. And if you can then do a simple analytical expression, both will give you the same answer. And one thing is you can run the computer for a certain period of time, shining light, letting the excitons go in various places, and then collect them. And another is to do this 2-line of algebra, and essentially you get the same thing. Now you can ask yourself, why do you really get the same answer? And the reason is this. A exciton which is generated here doesn't really care that this structure is complicated. And the example analogy I give is the analogy of a fly. A fly which sort of is born here, dies within 30 feet of where it was born. It's not necessary for the fly to know that the Himalayas exist, because the local topography, only thing it cares about is the local topography. It lives and dies within a very small distance, and therefore the complexity of the morphology has nothing to do with its life or how the excitons are generated and how it dies. So therefore, you can catch this essence of a very complicated transport argument in essentially a simple equation very nicely. Now here is a problem you can immediately see. If it is so great, if the excitant current in the beginning, it has a lot of area, if it is so great, then why should I anneal? In the beginning, I had a lot of surface area, excitons will get dissociated very nicely, I should not anneal. But it turns out that you should anneal, and otherwise the experimentalists would be wasting their time. So they have known by empirical methods that you should anneal. So what's the trick? What am I missing here? Now, the trick is the following, that actually, if you really look at the short circuit current that is coming out of the cell, out of a complex cell, that really doesn't go from a high value to a low value. Rather, it starts with 0. Now you wonder, why would it start with 0? And then it goes up, goes through a peak, and this is why the chemists and engineers who do not care about theory, they stop by doing using a lot of grad students. This can be empirically found. The trick is the following. The trick is that, of course, if this structure is thick, then there is a connected highway that will allow you to go to the proper contact. If the structure is on the other hand, so this allows you to get out, the holes get out, let's say. But if the structure, if there are islands like this, which will trap the electrons or holes, then they cannot get out. And what happens in these structures, yes, excitons can get out very easily, but the electrons and holes may not be able to come out through this complicated maze. So you increase exciton dissociation, but you lose out on electron and hole collection, right? And because you lose out on this, that is why there is an optimum. So this is a percolation problem for electron and holes, and so you get a lot of exciton dissociation, but as the electrons are trying to find its way to the other side, lots of holes are also trying to find its way to the other side, lot of recombination, and as a result, you really do not get much out to begin with. By the time you come about here, it sort of nicely balances the exciton dissociation with the electron hole transport. You have a maximum efficiency, a maximum short circuit current. And then if you stay too long, then these regions get so thick, then they get out very nicely, but they don't get dissociated very effectively, because these regions are thick, you are losing a lot of excitons. So this is a trade-off between resistance and current collection versus exciton dissociation that defines the maximum. So if you want to compare these various structures, you can see that the bilayer or the planar is the least efficient. This structure is somewhere in between, and the ordered structure, if you could make them cheaply, then that will be the in some way most efficient. But in general, this random structure is essentially pretty close to optimum if you can process it correctly. So let me then end with a few slides, and this is sort of the essential point. Remember what the problem I said in the beginning was, that this looks all very nice physics, you can write a PhD thesis and all, but of course you cannot sell a single one of them in the market because these are too expensive. And the reason it's too expensive, low efficiency, right? Few percent, 7-8% efficiency these days, and horrible lifetime. So 1 year you'd be lucky. So the question is, what can you do to solve that problem, right? That's the goal. At the end, we are engineers. Physics is good on the side. The real reason we do this is because we want to solve problems. So what can you do? One is use low band gap, new polymers with low band gap, because as Professor Lundström mentioned, Professor Gray mentioned also, that if you have silicon is almost optimum band gap, or gallium arsenide, this has too high a band gap, sometimes close to 2 eV. Of course, these are inefficient because lots of photons are just going through. So you can ask, well, what are all these chemists doing? The problem is that as soon as you try to synthesize new polymers with a lower band gap, not that you cannot make it, but remember, you have to mix it. Solubility is very important. And so far, people haven't found a way in which they can have a low band gap, 1.7, 1.6 eV, and at the same time soluble with respect to each other. That pair does not exist. So that is the problem in this technology, and people are trying very hard. If you have any idea or can come up with something, you will be very happy that it could be done. Some people might say that why not change the ratio of the blue and the red? 1:1 is good, but maybe the red one, if it absorbs all the light, generates all the excitons, then maybe I should make it 3:1 so that I can catch a lot of light and lot of excitons, and that will be good. But it turns out that the percolation theory suggests that you cannot go too far beyond 1:1. It doesn't really matter what you do, it's a geometry problem. And physics you can beat, geometry is very difficult to beat. You can say, yeah, we'll optimize anneal time, not very much you can do. And then you can do regularized morphology, but as I said, random maybe in some cases close to optimal. So you're in a tight box. Why percolation? Why 1:1 is very good? This is one of those organic material, P3HT, and then there is something called, the other phase is called PCBM. This name of two chemists, don't ask me what those acronyms mean, I do not know. The thing is that what you see that the connected volume of the percolating structure, of course when it's 1:1, both phases can percolate, because they have to each individually connect to their respective contacts. If they don't, then of course they are not going to, one phase is trying to get the electron out, holes are not coming out, you have zero current. So that's not going to work. And since in 3D the percolation threshold is 33%, at 33% they begin to percolate, it will turn out that close to 33%, the efficiency of the connected volume begins to fall very, very rapidly. So you cannot really go away from 1:1. There's no way the connected volume will arise. So in one phase, in one condition, all the blue will be trapped within this red, and they can dissociate exciton. They are not going to contribute to current. On the other phase, the red will be trapped in the blue, and again, you have no current. And in between, you have a connected volume. Both electrons and holes are coming out from their respective contacts. And the other thing is that you cannot even get here, because as you get close to this region, there's huge fluctuation from one device to the next. Sometimes it gets connected, sometimes it doesn't. And so remember, we have to connect them in series. So if one of them has lower efficiency and lower output voltage, it is going to kill the whole thing. It's like the shadow degradation problem. Here you have a lower current in one, and then of course that is going to sort of drag down everybody else connected in series. So therefore going away from this type of thing is very difficult. Now, one time I gave a talk in Columbia, and one of the chemistry students came up and said that if I knew this argument, I could get to my advisor and it would have saved me 2 years worth of work, because they had been trying to map out this whole thing, and he didn't have an argument to go and argue with his professor. Not that it's a good idea. Go and argue with his professor that why it didn't work. It didn't work, but why it didn't work, he didn't have a simple argument. So this was his argument, and he was very happy with it. The other thing is fluctuation. That is what I just mentioned, that organic solar cells, if you have a random structure, you have huge variability in the efficiency, in the short circuit current, in the fill factor, in the VOC. Why? Because every structure is slightly different. And so therefore, you'll have huge variability. So for example, this is WD is a function of the anneal time. The longer you anneal, the coarser it gets, right? All those regions are getting thicker. And so you can see that this whole trajectory is evolving. And each point is for one of the cells. Now, if you are interested in publishing in Nature and Science, or the important journals, you can try a lot of them and pick this one and publish. That will be fine because that shows that how much you could get in principle. But when you are going to connect a bunch of them in series and going to have a technology where you want to have huge volume, in that case, the efficiency you are likely to get is the average of them, if not lower. So in that sense, ordered structures make a lot of sense, because in the ordered structure, very little fluctuation, and this is always connected to the right contacts, so therefore very little fluctuation, and you can get very high efficiency, relatively high efficiency, and not suffer from this variability problem. So this is one of the challenges of organic solar cells. The fundamental nature of how an organic solar cell works, that makes this variability an inherent part of this. But of course, if your area is very big, your variability is going to go down, but your average is going to gravitate towards this average. So therefore, it really doesn't help you to have one data point in here and say that this is the potential of organic solar cells. So the last thing about reliability, and that's where I will end. So one thing is when I said that you process it in microwave oven or in your oven, but you have found recently that walking out in the open is no different than being in the oven, because these both temperatures are not so far but different. In the oven, it may be 125 degrees, outside 100 degrees. So for a solar cell, when you place it out in the sun, it doesn't know whether it's in the oven or in Arizona sun, let's say, or it still continues to think that is in the oven. Now, if it continues to think as an oven, what is it going to do? It is going to continue phase segregate. Yes, you stopped it, and you said that don't go any further, this is my optimum point, this all these phases and all, these are good, but then you put it there, and it begins to phase segregate because it thinks that you have accidentally put it in the oven. Now, if that happens, then what's going to So what's going to happen is that depending on the temperature, if you have 80 degrees, these are test temperatures, you have 100 degrees or 120 degrees, these are test temperatures, the phase segregation will continue, and if the phase segregation continues, what's going to happen, the width of these regions are going to get wider, exciton collection is going to get poorer and poorer, and in 1 year, for sure, the cell is not going to work. And this is the cluster size. Remember this T to the power 1/3 I told you about? If you made the temperature high, 120 degrees, then this is going to get faster. And on the other hand, if it's lower. So in Alaska, maybe things are better for the organic solar cells, but Arizona may not be so good. Now, so therefore, what you can do is to look at when you ship the product to the consumer, then what the W was, the width of this region was at that time, and how the W evolved as a function of time. You put the short circuit current, L exciton, that is scales with D to the power N, but now remember, this is the operating temperature, hence the word T naught, and this is the effect of the initial, when you ship the product, this is how long you annealed it. So when you put them together, you can get a simple equation that tells you that if you have soft material that can go through each other very quickly, which is the activation energy, if you put in the Arizona sun, then this whole thing is going to degrade very, very quickly with the exponent of n is 1/3. So this is to an extent you can actually predict how this is going to behave. You know, one thing you can say, this is degrading, I'll just measure it and plot a few points and send it out in a report. But here you can see, you can essentially say exactly that how this thing is going to behave as a function of time. And so what's going to happen? Your short circuit current is going to fall, and these are experimental data, and this is the theory that says that generally the trend is pretty well reproduced. And how much is this? This is in seconds. So this is couple of hours, and most things die within a month. So this is the reason why this happens, and you can calculate the lifetime. You'll be lucky if you get a 1 or 2 years. So that's how this thing works. Now, of course, this is not the end of the story. People are very clever. What they have done is that right after processing, there are photo cross linkers in here which essentially just before they ship it, they zap it with X-ray so that these photo-cross linkers create a container, sort of a network, which binds them in place. Now they cannot phase segregate when they are in Arizona sun. They want to, but this network of traps, then keeps them in place. That is how they have recently gotten 3 to 4 years projected lifetime. So, this is my summary then. Bulk heterojunction is good. Checkerboard is better. Checkerboard is better because you can essentially, it's always above the percolation threshold. Electrons go in their divided highways, they can recombine and you can optimize it. But of course it's going to be expensive. If you want to do it this top-down method, it's not like putting two things together. And then the structure like this, which Professor Agrawal's group have also worked on, this type of double gyroid structures is good, not because as a solar cell it can beat VOC or short circuit current or field factor in any way, because it cannot. You can mathematically show that the VOC of these three structures will essentially be all the same. But what it does is that it traps the phase so that it cannot phase segregate. Now many times, of course, the width is not really what you need, which is too small, so it doesn't collect excitons very efficiently. That's the problem with this structure. But other than that, if you could make it, this self-trapped structure would be the best, because this is above the percolation threshold, all connected, and then at the same time highly reliable. It will be highly reliable. Okay, so this is sort of the end of the story. So we said that the main reason we work on organic solar cell, and by the way, now if you go out, most of the universities and many universities, you will see very exciting work going on. The reason is not that this is a technology yet, but it promises to be a technology that is unbeatable. If you could do it, there'll be few things that will be better. And the most important thing is it's going to be very lightweight and it will be very easy to install. You can install it rather than having a company come in and install it. Now, I explained to you very simply that how percolation plays a role, how the reliability and the solubility, the same physics that governs phase segregation, makes it easy to work with, is the same one that makes it less reliable. So reliability and performance are flip sides of the same coin, and so therefore should be considered as such. And this variability I told you about, that when you have a series connectedness, is a fundamental aspect of our solar cells. And if the series connectedness, because of the series connectedness, you cannot have cells that have huge variability. Because if you have that, you lose several % of your efficiency by the time you connect them all up together, and that's not really very good. So the best solar cell that you might say for organics is how much? Maybe 8.1% or so. But by the time when the company wants to sell it, they cannot sell it to anyone. They sell it for bus stand and nice covers on the automatic, because it's not commercially viable. So in that case, they only get about maybe 3 to 4% efficiency. Very, very poor, nowhere near what it needs to be. Okay, but I suggested a few ways by which we can get to this 15% efficiency, and hopefully if we can do it, you'll one day buy your organic solar cells on your own. Thank you. Previous slide.
So we mix two polymers and then we anneal them and they do the sphenoidal decomposition. So is it on a substrate? What's the substrate?
The substrate is very important, but most of the work that I have seen done, this is on a small petri dish type thing, and the role of the substrate is not very clear, because what they say, because the physics is so sort of not well understood, and the nature of the phase segregation and all, what they generally do is they get a postdoc from a group that already knows how to do it, and then they exactly follow the recipe. But in general, people have been talking long about texturing the substrate so that you can grow these structures, monitor this. So there is a lot of work going on in locally templating the structure. So one phase or the other nucleates on that, and then that will also improve reliability. Yeah. But so far I haven't seen any result that would be called promising.
So in the previous lecture, I think you didn't mention about excitons.
Yes.
And certainly you introduced that, and it seems like it's very important for organic photovoltaics.
Absolutely.
Why is it so important only for organic photovoltaics or in general?
Right. So I went too fast in the very early part of the lecture. Should I go back to this one? I mean, I think maybe that's a very important point, because on no other solar cell we talk about exciton. And all of a sudden you're talking about exciton going this way, that way. That's very important to understand. Okay. You see, in order to highlight the importance, I made a joke about Professor Lundström that you should have considered his lecture fishy. And the idea was the following. When you think about, the main point I wanted to make was, exciton is the most natural thing to happen. Because anytime you have a photon coming in, electron-hole pair generated, they are on the same atom where the electron just got bumped up. Now you have this hole within a few angstrom. And this Q and minus Q is like a hydrogen atom. They should be circling around each other. Why should they go away? So going away is abnormal. Exciton is normal, right? Now, the argument I made was that if you look at the binding energy of how strongly they are bound, in the case of a hydrogen atom, it's in the vacuum. So your relative dielectric constant was 1. So you had 13.6 eV, and so if you didn't put a X-ray or something in it, nobody is going anywhere, right? It's very strongly bound. On the other hand, when you think about silicon dielectric constant is 12 or so. So look at this, goes as kappa squared. So it will divide it by 144, let's say in that case. Effective mass is 0.1. So what's going to happen, that instead of 13.6 EV, it is 13.6 milli-electron volt. Now 25 milli-electron volt is kT. So yes, they want to circle each other. If phonon comes in and kicks one of the electron, they forget about that they were excitons ever. They get out through their respective contacts. Not true for organic materials, because organic polymer have low dielectric constant. And because they have low dielectric constant, on the order of 3 and 4, this factor is not as big. And therefore, the value that you get, normal temperature cannot kick them out, right? And so therefore, and also this radius is such that unless you use a heterojunction, you cannot even pull them apart, because they are just close together and they are moving like together all this time. And then if you apply a p-n junction field, they don't care, because the PL junction field is a factor of 100 smaller than what you need to get into. That's the problem. Is that clear? Yes, please.
Can you use like a 4
Yeah.
In the two fluids, there was a problem of the trade-off between connectivity and the grain size. You could go for a 4 fluid with like two sort of like brotherly fluids, which would together form. You can have a 4 fluid solution in which the first 2 fluids form the correct grain size, and the next 2 fluids give you the connectivity. Is that a intractable problem?
First of all, I'm not a chemist, so I'm always a little worried about saying something. So the question is essentially that, can you decouple this exciton problem and the dissociation problem and the connectivity problem? But whether it is to the 0th order, and I will have to think more about it, to the 0th order, the percolation problem is very fundamental, that it has to connect to their respective contacts. So if you have 4, then let's say it has to be less than half and half, right? Because the other 2 phases will take care of. Let's say you have 0.4, 0.4 and 0.1, 0.1, 4 phase. Now because this 0.4 individually have to connect, so they may not be able to percolate.
The 0.1 is doing the percolation.
Yeah, no, but you need, in 3D, you need at least 33% of the total volume in order to percolate. On the average. So you cannot go below. In some cases you may be able to percolate, but most of the cases you will not be. It will be trapped within these pockets. Okay. So before